Here's a video discussing Newton's first law of motion, and I've taken a step away from the traditional definition. Let's take a look at it. Objects tend to maintain a constant velocity until they're acted on by non-zero external force. The traditional example talks about how a stationary object acts, as well as how a moving object acts. But in essence, they act the same way. Whatever velocity an object is traveling at, it wants to continue at that same velocity, even if the object is a stationary object. Look out in your yard, you might find a couple big rocks sitting there, and most likely they were there when you moved in. They just sit there. That's what rocks do best. And this is essentially what all objects in the universe strive to do. They are stationary. We could attribute a velocity to them of 0, and they've been that way since you moved in. Chances are, when you move out of the house, they'll still be there. Many years down the line, you'll look back at these rocks and they will still be sitting there. They have no velocity, or you could say they have a velocity of 0, and they want to remain that way. They want to keep that velocity. Is this a constant velocity? Well, of course it is. A stationary object has that velocity of 0. If it's always 0, then it's constant. This is what objects want to do. But not only do objects want to remain constantly stationary, they want to remain constant in whatever they're doing. So if we go somewhere else, say floating around in outer space with little meteorites, which are meteoroids, I think that's what they're called in space, floating around Earth, they're in motion and they're going around the planet. If you were to observe one of those, it would look like it's traveling in a straight line. It might come towards you, it might be moving away from you, it just might be passing out in front of your face. However, you'll notice that they are traveling with some velocity. As you observe the motion of these objects, you'll notice that they continue in a straight line. They don't speed up, they don't slow down. They remain at this constant velocity. Any number you could attribute to this, say something moving at 10,000 miles per hour, if it's out in space, it will continue at this constant velocity of 10,000 miles per hour. Now, where problems start occurring with this law is here on Earth. We don't see things like this here on Earth. If you go out, say, to a bowling alley with some friends, bowling alleys and bowling balls, they always look so happy. They got a little smile on their face. If you take a ball and you roll it down the lane, you would not expect that the velocity you give it, this slow velocity of some number, you would not expect it to continue on for its entire life at this velocity. If you threw it down the lane, it would either curve left, changing direction, it might slow down, it might eventually hit the pins and stop. We know that the velocity of this object will not remain constant for all of time. That's where the last part of this law comes in. An object wants to remain at a constant velocity, but much like everyone else, people on this planet, we don't always get what we want. The objects will maintain a constant velocity until something happens, and that until is that they will be acted on by a non-zero force. In other words, there is something that's going to be pushing on this ball to make it slow down. As it rolls across the floor, if you have a leftward spin, a rightward spin, or even no spin at all, there is going to be some friction acting on it. And friction always does one thing. It pushes the object in the opposite direction it's moving. If this ball is traveling to the right and it was actually on the ground, let's give a little hill to our bowling alley lane, it would be experiencing friction, and it's always in the opposite direction that the object is moving. Much like if you were trying to go down the alley and something was pushing you backwards, you would slow down. Well, the ball tends to do the same thing, and it is prevented from traveling at its constant velocity because there is a non-zero force acting on it. Now, why didn't we just say any force? Why didn't we say if there's a force acting on a ball, it would then not be traveling at constant velocity? Well, take yourself for example. You're sitting in a chair. I'm making an assumption, but I think it's safe to assume you're sitting in a chair as you're watching this video. As you sit there, you can ascertain or allocate a velocity for you. You say, well, I'm stationary, I have a velocity of 0. Does that mean that there are absolutely no forces acting on you? Well, we can consider this. The obvious one, in this case it seems you're levitating, let's assume you're actually on the chair. You are experiencing at least two forces. One of them you've been experiencing your whole life is a downward force that pulls you towards the center of the planet, gravity. And since it's a downward force, I'm going to say it's negative. Now, if this was the only force acting on you, you would go straight through the chair, you'd go straight through the floor, you would go straight down into the planet. Fortunately, unless that's something you aspire to do before you leave this planet, there's another force pushing you upwards. And if you look down, what you're sitting on, the chair is pushing up on you, supporting you, preventing you from going down. We have a name that you may know or may eventually start studying. We call this a normal force. And it is what is pushing you up against gravity. Imagine this is a tug-of-war match that's going on, where the mighty normal force is fighting up against the monumental gravity, and they are of equal strength. We have an immobile force against an unstoppable object. What shall happen? Well, not being so epic, if these are equal in strength, they will pull in opposite directions, and the forces will kind of cancel out. We can do it mathematically. The normal force and the negative g-force, if they're of equal size and we essentially end up subtracting them, this will balance out to a zero force. So you can have forces acting on you, but still have a zero net or zero total force. Alright, so objects tend to maintain their constant velocity. If they're stationary, they want to stay stationary. If they're moving at a certain velocity, they want to keep moving at the same velocity. And the only thing that's going to get in their way of doing that is if there is some type of external force acting on this. Whether it's gravity, whether it's someone pushing you in the back when you're lazily laying in a hammock in the afternoon, there has to be some type of net force acting on to change this. Okay. The last bit of this is that the force has to be external. You can apply forces to yourself. For instance, I don't suggest it, you could smack yourself in the face, pushing your face to one side. Now this is not what we can consider an external force. That would be an internal force. Any force a body applies to itself is considered internal. Any force acted by an outside object or an outside force is considered external. So while you might be floating around in space in a very thin spacesuit, I suppose you need a head. And your head's in here somewhere. Right. If you sit there and you push on your chest with your hand and you push yourself backwards, you will stay at whatever velocity you're traveling at, because that is an internal force. It's something you're acting on yourself. If another astronaut friend you're out there with, I'm not going to bother giving him a spacesuit, we're not worried about him. He takes a wrench and he throws it at you. As this wrench travels towards you and hits you, this force acting on you is considered an external force. This is not a force you're applying to yourself. It's a force something else is applying to you. This is an external force. This will cause your happy space-flying self, which was stationary with a velocity of 0, to change velocities to something else. You will no longer be happy at rest, staying at rest. Okay. Objects tend to stay however they're traveling until they're acted on by a non-zero external force.